to celebrate our country's 75th year of independence. It's my pleasure to introduce our speaker, Professor Jie Zhang, who will be discussing the initiation process of solar flares and also coronal mass ejections. Jie Zhang is a solar and heliospheric physicist and currently a full professor at George Mason University, Virginia, USA. He had been in this prestigious university as a co-founder of Space Weather Research in Physics and Astronomy Department of this university for the last 20 years and currently serving as the Associate Chair of Research in the department for the last 2 years. Professor G earned his doctoral degree from University of Maryland, USA, working under the mentorship of an Indian solar physicist, Mukul Kundu, who is known best as pioneer of solar radio observations of the sun. Soon after his PhD, Professor Zhang worked as a postdoc at the prestigious Naval Research Laboratory in Washington, D.C. He has been recipient of several reputed awards such as NSF Faculty Early Career Award in US, elected Cowley Fellow, Sigma Psi Honor Society, to name a few. He has led the organizing team of various international conferences and has been vice chair of COSPAR D2E3 commissions from 2012 to 2020. Currently, he is serving as a co-chair of the SOHO Presto, which is actually a acronym for Predictability of Variable Solar Terrestrial Coupling Program. He has also served as the leader of the widely known ICEST project, which is actually International Study of Earth Affecting Solar Transients. And he has mentored more than 10 PhD and postdocs who are now early career scientists at different institutes. So with this brief introduction, let's welcome Professor Jie Zhang. And now I request him to begin his presentation. Please, Professor Zhang.
Thank you, Vakish. Thanks for a very generous introduction. And I'm very glad to present in your institute, Indian Institute of Astrophysics. I see multiple familiar names. So I'm very glad to see you all. Hi, I haven't seen you for a while. So I hope I can see you soon in person, face to face. So today I'll be talking about the initiation processes of solar flares and the coronal mass ejections. As you can see at the bottom, there are two movies. On the left side is a movie of the solar flares observed by the ghost X-ray imager. On the right side is a movie for the coronal mass ejections observed by the SOHO LASCO spacecraft. So as you can see, sun is not quite. Sun produce these instantaneous explosions very often, multiple times a day during the solar maximum. And each of them contains the energy up to a billion atomic bombs detonated at the same time. So it's very explosive, very energetic. Now the question, how can sun produce such a structure which is unstable and which can release energy spontaneously and explosively? So this is what the things I want to address today. So here's the outline. So here's the outline of my talk. The first, I will give an introduction to space weather flares and the CMEs very briefly. Then we'll discuss the so-called solar flare myth. This is a paradigm shift in 1990s, about 30 years ago. Then I will be talking about what is the true relationship between flares and the CMEs. Then I'll be talking about the theoretical models of solar eruption and what are the models and what are the largest controversy in these models. Then followed by a discussion on the importance of the magnetic flux slope. I think magnetic flux slope is a deal breaker to distinguish different models. In the end, I will be talking about the so-called two-step initiation of solar eruptions. So this two-step initiation of solar eruptions actually add the confusion to which is intriguing to add it to the picture of understanding the solar eruptions. So in the end, some discussion and conclusion. So among all these topics, there's one fundamental question to be asked. What is the initiation process of solar eruption? For this initiation process, and I will further break down into two sub-questions. One is what triggers the eruption? what drives the eruption. I think the trigger and the driver, they're different. So I'll explain later. The space weather. So what is exactly space weather? I think there are many different the different way to determine to phrase the space weather, but this one is particularly good. It's in 1997, issued by the National Academy of Science in the US. So space weather describes the conditions in space that affect the Earth and its technological systems. I think this summarizes the space weather in one sentence. And also in 1997, the space weather formally became a discipline in scientific research. Prior to 1997, that was the year year I was still in graduate school. The people really heard the word of space weather. However, since 1997, the space weather become a buzzword, and it integrates the traditional communities such as the traditional solar physics community, traditional heliophysics community, traditional community in the ionosphere, magnetosphere, upper atmosphere. However, the space weather integrates everything of these more traditional scientific communities. So as you can see, space weather addresses a large system, from the sun to the Earth, and also including planets in the heliosphere. And it's a huge system, and it has multiple scales from centimeter scales in terms of the understanding magnetic reconnection and accelerating particles, to the larger scales such as hundreds of the millions of kilometers, such as the CME scale. So this is a very complex system. There are many things to be studied. So the impacts of the space weather on technological systems, besides the scientific interests, is huge. Almost all the spacecraft in space are affected by space weather, also affecting the communications through the disturbance in the ionosphere. So one good example, it just happened last month. The SpaceX company lost 40 Starlink communication satellites because just a moderate geomagnetic storm coming from a slow CME from the sun. Of course, there are multiple reasons contributing to the failure, but one of the important reasons for the failure of the 40 satellites was the space weather effect. Certainly, because of the importance of space weather, now the national space agencies invest a lot of effort in studying the space weather. This is on the right side, this is a collection of the spacecraft currently operational to study the Sun-Earth system. It's called the heliospheric system observatories. About 20 of them, and I'm glad to know that the Aditya L1 mission from India is going to be launched very soon. And also, I know that the Chinese version is called the Advanced Solar Observatory underscore SOS, is also going to be launched probably end of this year or maybe early next year. So the two more spacecraft will be joining this fleet, one from India, one from China. That will be interesting. All right, so let me do a little bit of advertisement. Recently, with a lot of co-authors, almost 20 co-authors, we published a very comprehensive review papers with probably more than 100 pages and more than 1,000 references to summarize the so-called Earth-affecting solar transients, to address what are the things coming from the sun which affect the Earth. So in this review paper, we identified 4 different types of transients could affect the Earth, including the number 1, solar flare, number 2, CME, and including the interplanetary CMEs called ICMEs, and the SEP, solar energetic particles, and also including number 4, the stream interaction region or the rotating interaction regions. And among all these 4 types of transients, we also identified in the summary table the key physical processes For example, for CMEs involve many physical processes such as the ideal MHD instability, flux loop formation, shock formation, particle acceleration, aerodynamic drag, CME interaction, and the magnetic reconnection. And each of these phenomena has effect on the geospace environment and also environment across the heliosphere. Because of this affects this environment, the impact, it has the impact on the technological systems. So on the last column, we highlight the effects on the technological systems. So just to do an advertisement, if your students, young scholars want to study the solar physics and space weather, I think that this is a good reference to start with, because this essentially summarizes all the transients could affect the space environment. All right, so a little bit of history on the solar flares and the CMEs. So the solar flare, even though space weather is relatively new, is 25 years new science discipline, but the study of the sun traced back a long time ago. The first solar flare was discovered, as you know, in 1859. It's about more than 160 years ago by Carrington, when he used a small telescope in the backyard to observe the sunspots and accidentally discovered a flash within the dark sunspot. As a white flash occurred, then disappeared. On the same day, one of the largest geomagnetic storms registered on the surface of the Earth. This Carrington event is so famous. Probably this is the largest solar eruptions, the largest solar eruption in the last several hundred years. And there are so many things needed to be mentioned, but I just want to mention that, you know, the aurora was so bright, as mentioned in this newspaper. The people at Boston can read the newspapers under the light of the aurora. You can see that's how the aurora is so bright on that day. And also, this event disrupted the latest technology then, the 160 years ago, that is telegraph lines. So they were affected by this disturbance. So that is the flare. Then, however, for observing CMEs, it came very, very late. I think the first space-based observations of CME came in 1971. So this is the 1971 event that happened about 50 years ago by the orbiting solar telescope 7 OSO 7. I think that was the dawn of the observing the CME from space, because the observing CME from the ground is very difficult. Maybe just a guess, you know, maybe over the history, when people observe solar eclipses, they may see the CME like this cartoon showing on the right side. But nevertheless, you know, solar eclipses are rare, and observing the CMEs over the solar eclipse even more rare. So CME observations are largely from space, but of course you can observe from the ground, but then the quality would be much less than from the space. So the CME observed came later, much later than flare. But then there's an interesting thing to people maybe ask. So what causes the disturbance on the Earth? So what is the causes of the auroras? What is the cause of a geomagnetic storm? Well, in the before 1990s, you know, there's a so-called the flare-dominated view. People have a perception that everything is caused by solar flare, by large solar flare. So this is called a solar flare myth. It's criticized by Jack Rosling in this 1993 paper, and he pointed out that, well, the flare is not at the center of this Sun-Earth connection or Sun-Earth transient study. So what is at the center of that should be coronal mass ejection. Because since the 1970s, there were many observations that always pointing at that CME has to be present in order to have a geomagnetic storm. So indeed, in 2007, we had a paper studying all the intense geomagnetic storms over one solar cycle. And as you can see, for all these 88 intense geomagnetic storms, the 54 events originate from active regions. Only 36 events are associated with X and M-class flares. So only 36 out of 88 intense geomagnetic storms are associated with X and M-class flares. That means more than 50% of the intense geomagnetic storms are not associated with any major solar flare. So this basically removes the flare from the center of the Sun-Earth connection. So what is the current paradigm for the Sun-Earth connection or the cause effect of the space weather? Well, of course, now the common sense is the CME should be at the center. So CME is at the center along the cause effect chain between Sun and the Earth. And also the essential physical structure of the CME should be a coherent magnetic flux loop. We know that in order to have the occurrence of intense geomagnetic storm, a CME hit is required for that occurrence. So on the picture on the left side, also coming from this review paper, we just summarize the observations on the Sun, the CME, and then the cartoon model for the CME and the driven shock in the interplanetary space, and then it arrived at the 1 AU from in situ measurement of the solar wind. Essentially, a CME has two fronts. So one front is ejector front. The front is caused by the expansion of a magnetic flux loop. So I will discuss more about a magnetic flux loop later on. But this expansion of the magnetic flux loop is the underlying magnetic structure of the CME. And then the expansion drives the shock ahead of it, which in turn accelerates energetic particles. So this is a basic picture of the CME. So eruption from the Sun. This is a basic picture of the geomagnetic storm. The cause of it is from the Sun and all the way to the Earth. Those are the essential observations. So then what is the true relationship between CMEs and flares? Well, before 1990s, so people realized that CMEs and flares are associated. But the study, because of the cadence of observations of the CME, were very poor. You may have a CME image, but it take half an hour and 1 hour to have one image. Because of that, the people found out using extrapolation of the CME timing back to the surface of the Sun. They found that the CME can occur randomly around the time of the flare. So the conclusion by Harrington in 1995 says that, well, CME flares are signatures of the same magnetic disease. So they are coming from different parts of the magnetic structure and to a particular activity. They do not drive one another, but are closely related. So I agree with that assessment. They do not drive one another, but are closely related. But then question, how closely they are related? It turns out they are very much closely related. So when I graduated from, got my PhD from the University of Maryland, and then I went to Naval Research Lab. That Naval Research Lab is the PI institute for all the coronagraphs. So I spent a lot of time studying CME initiation, and then I noticed that the early CME leading front. So I measured the early CME leading front from the SOHO EIT images and also from SOHO LASCO C1 chronograph, tracking their location with time. So the dot here is the location or height of the CME with time, and the black line is the ghost X-ray intensity. At the bottom shows the velocity of the CME and shows the intensity of the ghost X-ray again. So if you compare the velocity of the CME and the ghost X-ray intensity of the flare, astonishingly, we discovered that there's a time coincidence between the CME acceleration and the flare energy release. So it's not just a simple coincidence. They occur almost at the same time. So I was really surprised back then, and I submitted the paper to the APGA. I got rejected because the referee doesn't believe that, because they said, okay, CME could happen earlier after randomly around the flare timing. So this kind of simultaneously, maybe due to just the measurement uncertainty, something like that. Well, we fought back, and eventually it got accepted by the APGA. Then later on, in a later paper, 5 years later, we by studying many events, we found out such a common relationship between CME timing and flare timing, and then came to this kind of summary of the relationship between CME and the flares. So instead of CMEs and the flares are related, but it's more than related. CME and the flare are strongly coupled in the energy release process. You can see that based on this kind of the illustration, the velocity increase of the CME is always synchronized with the flare flux increase, and the CME velocity reaches the peak velocity more or less at the same time as the ghost X-ray reaches the peak time, and also the onset time is the same. So it's more than related, it's strongly coupled and maybe synchronized. So because of that, we think the CME and the flare can be collectively called a solar eruption. So I'm happy that now solar eruption has been commonly used, because solar eruption can mean CMEs and flares are two different phenomena of the same eruption. Also, in that particular illustration, we point out that for each eruption, there are 3 phases: the initiation phase, the main phase, and also the propagation phase afterwards. So I will come to this initiation phase and the main phase later on in more detail. So CME and the flares are strongly coupled. They come from the same solar eruption. They're almost synchronized. Now, the question is that it's not the initiation of flare, it's not the initiation of the CME. The question is that what is the initiation process of a solar eruption? Again, two sub-questions. What triggers the eruption? What drives the eruption? Well, their standard model over there developed in 1960s, 1970s, largely to explain the solar flares. So this is called a standard model of solar eruptions. If you do solar physics, you know that. It's called a CSHKP model, the acronym of the 5 authors of these 3 classical papers. In all these papers, they involve a bipolar magnetic field configuration with a dynamic current sheet that undergoes magnetic reconnection. So in this standard model, you have a bipolar field, and then you have the current sheet forms underneath this kind of twisted flux substructure in 2-dimensional representation, then produce all kinds of the phenomena as observed. So this is a so-called standard model. It has this kind of a magnetic configuration, and the key driver underneath is the magnetic reconnection. So through magnetic reconnection, you reduce the total magnetic energy in the system. So this magnetic energy is converted into multiple things, into particle acceleration, into plasma heating, and also could be into the driving of the motion of the plasma in the system. So just let me show you one movie to see how nice this the standard model looks like. So this is the one of the CMEs, one of the observations by the advanced solar dynamic observatory, the most well, not the most. So this is a very advanced telescope observing the sun in very high cadence, highest temporal resolution, high spectral resolution, and also multiple multiple pass bands. So this is a solar flare. You can see the flare is over here. That's the impulsive phase. This is the decay phase. Then you can see the flare ribbons over here. The flare ribbons in all the temperatures, from 1 million degree, 2 million degree, 3 million degree, all the way to 10 million degree, and also transition region and a photosphere. So the classical CSHKP standard model can explain all these phenomena, including impulsive or fast energy releasing solar flares, produce hard X-ray, gamma ray, radio. This classical model, standard model, can also explain the expanding flare ribbons, also explain the post-flare loop arcade in mixing H alpha and EUV and UV, and also can explain the long duration of soft X-ray because of the closing down of the opening field. So this standard model is good, is so good. Then what is the problem here? What is the controversy? So the controversy is that the standard model, which is essentially 2D when it is created, invokes magnetic reconnection that releases stored free magnetic energy in the corona and drives the eruption. However, it does not specify the 3D configuration. It does not specify what triggers the eruption. So basically, it explains all the phenomena during the impulsive phase. However, it does not address the trigger of the eruption. Actually, afterwards, in the last 30 years, there are many models developed, but all these models, they diverge or different in these two issues. What is the 3D configuration of the magnetic structure? What is the trigger mechanism for the eruptions? So since there are so many models, I grouped them into two camps. The camp A, the group A is magnetic reconnection triggers the eruption. The camp B says the ideal MHD instability triggers the eruption. Nevertheless, this camp B model, the ideal MHD instability triggers eruption, requires the presence of a coherent magnetic flux loop. So the magnetic flux loop is the key now to differentiate the two different types of models. So I'm just giving you examples of for the group A, camp A, the magnetic reconnection triggering models. There are different variants, including this analytical model. It's called a catastrophe model, which is an analytical model in 2-dimensional. Also, this cartoon model, called a test cutting model, involves a sigmoid in 3D, but also it requires the magnetic reconnection to drive everything. And also the famous breakout model that involves a quadrupolar magnetic field with a null in 3D. But in this model, it also requires the magnetic reconnection trigger the eruption. On the other hand, the camp B, the ideal MHD model, strongly proposed by Jim Chen and Tibor Torok and Klim Bernhard, they think, well, the flare is not needed. What you need is a presence of the magnetic flux loop like this. And if the magnetic flux loop exists, what triggers eruption is probably so-called torus instability, because the presence of the magnetic flux loop, it has its own Lorentz force. This Lorentz force is called a self-Lorentz force. It's described by the terms over here. So the self-Lorentz force over here, also called as the hoop force, it naturally drives the structure outward. And the overlying field produces a strapping force will push the flux loop down. So the balance between the hoop force of the flux loop and the downward strapping force from the overlying field balance the flux loop. However, if the flux loop grow over time, slowly reach a critical moment, is called an instability moment. Then, if the flux loop further increase the height, the decrease of the hoop force will be smaller than the decrease of the strapping force. So this will trigger the instability since when the flux grows, the outward force is always stronger than the downward force. So then instability happens. And nicely, the Klim Torp paper, they derived a simple criteria. It's called a critical index. So this critical index describes the gradient of the magnetic field of the surrounding field. So if this gradient is more than a critical number, roughly 1.5, the system is unstable. So these are the two ideas, the magnetic reconnection driven or trigger and the ideal MHD trigger. So which one is correct? So this hinges on an understanding of the magnetic flux loop. So what is a magnetic flux loop? Well, there are many ways to address this issue. So one picture you see here on the left side, this animation here shows the magnetic flux loop envisioned by the extrapolation of the active region field. I know some of you, especially when already knows how to do that, and he's very good on this. So essentially, the magnetic flux loop is a twisted structure. So the field lines twist around the central axis, at least one turn from one turn of twist from end to end. And also, flux loop contains a current channel, which is 3D in nature. So I want to point out that the magnetic flux loop is not a current sheet. A current sheet is essentially a 2D structure in morphology or topology. But the magnetic flux loop is a 3D in topology. And also, magnetic flux loop is not a sheared arcade. The sheared arcade has no twist. It only sheared, but no twist. So the difference between the current sheet, the flare, the flare related to current sheet, there's a difference between the sheared arcade, the difference between these two with the magnetic flux loop. Interestingly, magnetic flux loop was not discovered on the sun. It was first specifically mentioned and discovered in situ by solar wind observations in 1980s. In solar wind in situ observations, when you observe the magnetic field of solar wind, you can see the enhancement of solar wind. Enhancement of magnetic field in the solar wind is called a magnetic cloud coming from the sun. And then for this magnetic cloud coming from the sun associated with CME, you see the rotation of the magnetic field. Typically, the magnetic field only has the BX, BY component, but when a CME occur passing the Earth, you would see the rotation of the field with the BZ component that appears. So this magnetic cloud then can be reproduced or modeled by this so-called the Lundquist solution, this solution here, to produce a helical field, to reproduce the field as observed. So this kind of modeling can be used to further infer the global structure of the CME. So this flux loop structure you see in the interplanetary space, as shown here, actually provide us the basic understanding of the CME, because the flux loop is believed nowadays, it's commonly believed is the underlying magnetic structure of the CME. So next, so we understand the flux loop from in situ observations. Now, what is the observational signature of the flux loop from the sun? Well, you know that we have a lot of solar observations, but what are the observational evidence of the flux loop? Why the flux loop is still a mystery to us? Well, you can see there are so many observations, such as observe the filament. However, is a filament a flux loop? The answer is yes or no, because depending who you are talking to. Some people say, okay, it's a flux loop, and you can use models to reproduce the filament using a flux loop configuration. Some people say, no, you don't have to involve the flux loop. Sheared arcade also can produce flux loop. So I provide a reference over here. So there's two different groups over here to interpret the filament. Is whether a flux loop or not. The other one is sigmoid. Sigmoid has been observed for the last 30 years. Is sigmoid a flux loop? Yes or no? But I think most people believe sigmoid is a flux loop. However, the problem is that the X-ray observations of a sigmoid, typically you see a transition from sigmoid to arcade. That is, you can see a sigmoid in X-ray, and after the eruption, it become arcade low down in the corona. You cannot see the continuous transform from sigmoid to a flux loop and expanding out become a CME. So in X-ray, it's hardly you can observe, sigmoid to flux loop to a rising and expanding flux loop becoming CME. So that's why even though sigmoid has been observed, but there's no direct evidence to indicate that this is a flux loop. Fortunately, since the launch of the SDO spacecraft in 2010, we had a lot of interesting data from SDO. I think a lot of us benefited from SDO data for our career, right? So this is one of my benefits. We observed we think we have the best observational evidence of the flux loop, which is based on this. So again, this is a bunch of CME movies of one eruption, both X-ray profile on the top, and the multiple panels here shows the movie of the eruption. Let's focus on this panel, the panel on the lower left, and also focus on the timing during the flare impulsive phase. What do you see here? So let me move up and down here. So I move the cursor to the timing of the beginning of the flare, then come down to the early flare. So if I move back and forth, you can see that there's a structure erupts. So this structure is a low-lying structure as the flare after the flare onset. You can see it rises and expands, and it become a kind of semicircular structure. It's just look like the concept of a flux loop, of flux loop. They expanded out. So this expanded out will definitely become a coronal mass ejection. So the coronals are observed in multiple temperatures, from 1 million degree to 10 million degree. But this kind of structure, the flux loop structure, or we call it the hot channel. So we coin the name as EUV hot channel. We call it hot channel. So this hot channel can be only seen in 10 million degree, maybe sometimes in 6 million degree, but never you can see it in 1 million degree or cooler temperature. So to further make my point, I showed the same event using these two figures. So on the left side is if this the hot channel structure we believe is a flux loop in 10 million degree at the same time and the same location. What are you seeing? Cool temperature is 0.6 million degree. You don't see anything of the flux loop over here. What I see is a cool coronal loops. So this cool coronal loops is not erupted. It's just to be pushed outward. But you can see in low temperature, there's absence of this hot channel in cool temperature, but in the hot temperature, there's absence of the larger scale cool loops over here. So the coronal loops can see in cool temperature, but not in hot temperature. The flux loop can be seen in hot temperature, but not in cool temperature. So this is why before the SDO mission, even though we have EUV observations from the EUV observations of corona from the SOHO EIT and STEREO EUVI for more than 15 years, we have tons of the EUV images of corona, but we never discovered the hot channel or flux loop for 15 years because unfortunately, these two EUV instruments, they don't have a passband observe the hot temperature corona plasma. So why I believe that this feature on the left side is a flux loop? Three things, because it is a single coherent structure with fixed foot points, and also is a continuously, that's most importantly, it continuously transforms from a sigmoid to a semicircular shape and moving out is a typo here. So unlike the sigmoid in X-ray, the EUV hot channel you can see being continuously transformed from a low-lying sigmoid to a semicircular shape and then moving outward, becoming the CME. And also it only appears in hot temperature. So this is a unique character of the flux slope. So tracking their kinematics. So this one tracking the hot flux slope, the leading edge over here on this this red line, and also we track the cool corner loops as in this line over here. So if you compare the height of the cool corner loops above the flux slope is this one, and also this is the flux slope below underneath the expanding corner loops. So the corner loop is higher than the flux slope because flux will start very low from the corona. But if you convert the height into the velocity, you can see that the velocity from these red points indicate the velocity of the hot channel of flux slope. The velocity is higher than the cool corner loops. So it means that what drives the system? The drive of the system is the erupting flux loop, is not the cool loop. The cool loop is just simply be pushed outward by the erupting hot channel. To reinforce this idea, just give you another example. So you can see this is another movie for the hot channel or the rising and expanding flux loop, and so we see many of such movies. So I'm fully convinced that the flux loop exists before the eruption, at least for some events. May not be for all events, but for some events, definitely flux loop exists prior to the eruption. So you can see this observational picture in the middle here. Amazingly, it's very much vividly similar to the cartoon model, cartoon picture showing on the right side, which was made in year 2000 by Terry Forbes. In that paper, Terry Forbes paper 2000, it only provided the black and white version. Then Peter Gallagher had a new version, which is a colored version on this on the right here. You can see this flux loop or hot channel, similarly to this feature showing over here, and underneath is the region of magnetic reconnection. Then further underneath is the post-eruption loop arcade, and then ribbons are at the foot points of the loop arcade. So this is exactly as observed. Remember, this picture cartoon model came from the idea of the standard model. It means that a standard model is pretty good. So since it's 1:45, I still have some time, I think. So last topic, we'll be talking about the complexity here, the two-step initiation of eruption. So the CME or the solar eruption initiation is not a single step. It has two triggers, trigger 1 and trigger 2. So the trigger 1 is to produce the slow rising of the erupting structure, and the trigger 2 triggers the fast rising of the erupting structure. So it's not unlike you shoot a bullet. You just have a single trigger, then it will be launched. Or you launch a rocket, you ignite the rocket will be launched. CME doing something very interesting. It has two steps. When you trigger the eruption rises slowly, then it has to wait later on by 10 minutes, sometimes even 1 hour, then something happens, then it becomes shooting up quickly, exponentially increase the velocity. So there are two steps of the evolution during the initiation and the two triggers over here. And to prove that, let me show you how I verify this. So this is a collection of the flux loops. If you like to watch the movies, here the movies, as you take a look, these are the 4 different UV hot channels and flux loops. They are very similar, but they're all seeing 10 million degree. So basically, we can track the height and the velocity of these features every 12 seconds. Since the SDO is so great, it provides such an image every 12 seconds. And also we for all the events of the hot channel coming from active regions, but also there are some events coming from the quiet zone region, the filament channel. So we also track the evolution of the filament eruption at becoming CME. So both filament and also the EUV hot channel can be used to track their kinematics. So this is what we get. So we started 6 events of hot channels and 6 events of the filament eruption. And you can see all the hot channels coming from the active regions, they're associated with flares. And these 6 filament eruption we started, they're coming from the quiet zone region. There's no flare associated. All the events are associated with CMEs later on, but only one of it is a failed eruption. So what are the 2 steps look like? So this is the on the left side is the example of the EUV hot channel. On the right side is example of the filament eruption. You can see that this velocity, you can see the velocity is very slow. It's nearly constant for a while, then become in a sudden way during the onset of the flare. That is, the red line shows the onset of the shows the echoes X-ray. So you can see onset of the flare occurs over here. So only after the onset of the flare, then the CME starts to rise up quickly. Before that, the velocity is more or less constant. Same thing over here for the filament eruption. The velocity is more or less constant for a long time, for more than 1 hour. Then only after the thermal emission increases. In this case, since there's no X-ray observed, so we use the AIA 304 flux as a proxy of the X-ray. So only after the 304 flux suddenly jumps up, then the filament starts to rise quickly. From these observations, we are further convinced that during the impulsive phase, or the step 2, CME and flare are synchronized. So during the impulsive phase or second phase, their evolution are more or less synchronized. So that means they're locked step by step. So they're driven by a positive feedback process because flares are associated with magnetic reconnection. CME or the flux rising are related with the ID or MHD instability. So this process are step by step, they're synchronized. So it means that there must be a feedback process with them. Basically, the rising motion of the flux loop will make the reconnection faster because the current sheet becomes thinner in the current sheet. But on the other hand, when the reconnection is faster, it will produce a more colloidal flux into the flux loop, make the flux loop become more unstable, then rising even further. So this is a positive feedback process between the flare energy release through the connection and the CME rising or the flux rising through the so-called instability or the self-Lorentz force. So with that, we fit the kinematics by a curve. So we tried a different curve for fitting the height time data, and it turns out that the best curve is this one. So the whole evolution of the structure can be described by this equation. It has a linear term. It also has exponential term. So this exponential term basically describes the second phase, that's the explosive phase, how it evolves with time. This linear term basically describes the first phase before the fast acceleration, the slow phase. The slow phase, because it's the linear term, the slow phase can be more or less be characterized by a constant speed, because this function describes the height versus time. So the linear term means that the velocity in the initiation phase is very constant. So with that, for the 12 events, we have this number. So for the for the hot channel for eruption from the active regions, we found that the slow phase lasts for about 10 minutes for hot channels. However, for the filament eruption, the slow phase can last for a few hours. So for filament eruption, the slow phase allows the last for a few hours, but for hot channels from active regions, it only lasts for about 10 minutes. There's also difference here in terms of velocity. For the hot channels, the average velocity is about 30 kilometers per second. Then for the filament eruption slow phase, the average velocity is only about 5 kilometers per second. So that is a conclusion about the two phases or two steps evolution of CME of the initiation of solar eruption. So this is very interesting, and we don't know how to explain that. So now let me come to my conclusion. So the conclusion one is that the standard CSHKP model is generally valid, remain to be valid even after 50 years of tests. This standard model is still valid at large. It's just further enriched by modern studies. So you still the essential components of bipolar configuration like this, and the current shift underneath, reconnection over here, the flux loop at the top, and then reconnection drives the post-eruption arc and ribbon, and then the instability produces the rising motion of the flux loop, and then further on it drives the shock. So the whole picture still, I think, is pretty similar to what people envisioned about 50 years ago, but just with more flavor into that. So that's my conclusion on the standard model. Now, what are my answers to the two questions? What triggers the eruption? What drives the eruption? So the answer to the second question is I think is definitive, and I think is also be accepted by most people. The answer is that to drive the eruption or the main phase is driven by a positive feedback process between magnetic reconnection and ideal MHD instability. So that is the driver of the eruption. Then question is that what is the trigger of the eruption? The answer is not definitive, because the trigger is not a single trigger. It has two triggers: trigger of the slow phase, trigger of the faster phase. Then what is the process? So right now, I personally believe that the slow rise phase is possibly triggered by ideal MHD instability. The main phase is triggered by the onset of fast reconnection, but I'm not fully convinced by this scenario. I'm sure some people in the audience may have different opinion. Maybe the truth can be reversed. That is, the slow rise phase is triggered by reconnection, and the faster phase is triggered by the instability. I talked with Tibor Torok and Bernhard Klim. They believe that the faster phase is triggered by the instability. So the answer to the first question is still open, I think. Let me leave it this way. So finally, I just want to show that here I talked about the initiation process of the CME, but then another question is looming large, is that how can a magnetic flux form? So is magnetic flux formed during the emergence from subphotosphere, or during the flux cancellation in the photosphere, or from the reconnection in the corona? So there are three possibilities. Hours ago from the subphotosphere, then from the photosphere, then from the corona. We don't know yet. It could be formed days, hours, minutes before the eruption. So we don't know yet. So these are all also open questions to be investigated. But I'm hoping with more observations, such as from the CAST, such from the even the Aditya L1 mission and SOS mission probably can provide a more definitive answer to these important questions. With that, I conclude my presentation. Thank you very much, and that's it.
Thank you very much for this very interesting talk and giving the connection between the flares and the CME and the trigger and the acceleration part of the CME. I enjoyed the talk very much. I invite audience to ask questions. So if you have a question, you can raise hand and then you can unmute and ask the question directly. And if you don't want to ask directly, you can also put your question in the chat box. So I will read it and direct it to the speaker. So there, I see the two raised hand. One from Vema. So Vema, go ahead and ask your question. Unmute yourself.
Hi Ji, very nice discussion on CMEs and flares and their initiation processes, and I enjoyed it. Okay, so regarding the flare and CME, that is a flux rope, when we are talking about the lower atmosphere and their synchronization during the rise phase, when this is happening, so can we expect the type 2 and type 3 bursts will happen same time? Can we observe them same time?
The type 2, of course, type 3, type 3 is caused by the energetic particles. They're associated with the flare. So I think type 2, the timing of the type 3, the timing of type 3 should be at the same time as the solar flare. But type 2 radio burst is tricky because type 2 is caused by the electrons in the shock. The shock, even though CME is initiated, the shock may come later. The shock needs some time to develop because CME is accelerating. In the very beginning, CME is not fast. So you have to wait, maybe 10 minutes, 15 minutes to have before the shock can be fully formed and then produce a type 2 radio burst. So if you study time, I guess you know better than me, the timing between type 2, type 3, they're not the same time, right? The type 2 may be later than type 3.
Right, yes. Yeah, so what my intention is that, so knowing the fact that the CMA is followed by the flare, so at least in this flux rope scenario, we expect type 2 burst come first and followed by type 3. Okay, so but this is not the case in a large number of cases. So for example, whatever type 3 and type 2 data you study, so this is not happening in some of the case, such that we can generalize the events just by seeing the radio data to attribute it to the flare, the flux rope and the flare scenario. So that's my point. Thank you.
Okay, all right, yeah.
I see Bhuvan has raised hand. So Bhuvan, you can unmute yourself and ask question.
Thank you, Jayan. Yeah, I am Bhuvan Joshi from Udaipur. So thank you very much, Dr. Jie Zhang, for a very nice overview of this flare CME coupling and the processes involved there. So I have a question about the step 1 that you described when the flux rope evolves slowly.
Yes.
So, and you gave a scenario that probably, of course, I mean, the other group will not agree. I mean that in the step 1, probably it is ideal MHD which works, and in the step 2, we have fast reconnection, and that supports the strength of the flux rope. So there is a feedback between the two processes. So my question is about step 1. So in case when we do not see any brightness enhancement before the main eruption, that is during the step 1. So when you have the slow evolution of flux rope, we see this pre-flare or precursor brightening in the flare.
Yes.
So suppose a filament or a flux rope erupts suddenly, that is, there is a fast reconnection before any pre-flare kind of activity. So how we explain those things, or we can, I mean, my question can be put in another form, that can we have the onset of fast reconnection without any pre-flare processes or without the slow evolution of the flux rope?
I think really there may be a few events they don't have slow phase, but for these events they are very explosive. So if the slow phase only lasted 1 minute or 2 minutes, you won't be able to notice it. So I think this slow phase is quite common. Now the question is that of the precursor phase. I think you raised a very important question, the precursor phase. Without CME studies, people have been studying solar flares. They noticed that some flares have precursor. Such as there are multiple precursors, such as the small bumps in X-ray profile. Sometimes you see the small type 3 radio burst. In some extreme cases, you can even see hard X-ray burst before the big flare happens. So they are quite a precursor phase. So is a precursor phase that is necessary for the big flare to happen? No, because a lot of flares you don't see the precursor phase. It only happens sometimes. So this makes this picture really still fuzzy. It's not the very sharp in terms of the precursor study. But on the other hand, so that's why we started this event from the angles of the kinematics. So without worrying about looking for precursors, so we don't know if there's any precursors for these events or not. I think if you look deeper, I definitely you can find some examples have the X-ray bumps there. And also, I think for some other events we investigated, we noticed that the precursor happens is the brightening, not for all the events, for a few events. The brightening happens before the major flare happens. What's going on there is actually the one leg of the flux loop rise up asymmetrically, not the whole flux loop rise at the same time, but the one leg rise up first, the other leg still remain untouched. So the asymmetrical rising of one leg pushing up the overlying field of that particular leg, and then interaction between the asymmetrical rising of one leg with the overlying field and reconnects there, produce these small bumps of heating. So this heating is not a global fitting, permeates the entire flux loop, only is a localized heating. So there are a lot of interesting things going on. You can always find the cases you like. But the question is, what is a common thing? What is the common thing underneath? So it's the open question, I think.
Yeah. And one scenario could be, this during the slow evolution, two things are happening simultaneously. We are having this ideal MHD processes, which will, cause the slow evolution of the flux rope. But at the same time, the flux rope is, building up by tether cutting process or a smaller scale reconnection.
Yeah. The tether cutting, the precursor phase, I don't know, it's a consequence of eruption or a consequence of rising, or is a cause of rising. So chicken and egg, you don't know which one. If you think the reconnection drives the slow rising, then the reconnection is the driver, or is the trigger of the rising. But it could be it is unstable, this because unstable push the formation of the contact sheet produce a small scale reconnection. So either way can be explained. Yeah, I think one of my goals is to look more signatures to find out which one is the true trigger.
Thank you very much.
Yeah. I see Vagish.
Questions.
Yeah. So Vagish.
Yeah, so hello, very nice talk actually. So I have two questions, one regarding the pre-existing flux rope and another on the kinematics. So first question is it possible that like the arcade in some case can be converted into flux rope having a strong twist? Means in extreme cases, the ordinary flux rope can be converted into twist in the flux rope. Is it possible that?
You mean the arcade can be converted into twist?
Yeah, if the arcade gets very strong twist, can it be like called flux rope? Means how we define flux rope? So it's like that.
So that's a very tricky question. You know, we the Pastorakos et al. On the course of that, we had a review paper in 2020 published. That paper, you know, is coming out of an EC team discussion. Just want to address the question: what's the difference between the shield arcade and the flux loop? In that paper, we defined that, you know, in the solar physics, unfortunately, the difference between the flux loop and the shield arcade observationally is difficult. You know, there's most of flux loops, even though you know think of the structure of the flux loop, they're not strongly twisted. Maybe it twists by 1 turn and 2 turns. Why is that? If you have so many turns of twist, it becomes kink unstable. But we don't see many CMEs, we don't see many kink unstable phenomena happens. We just see the flux loop lifts. So that you don't see much kink there. That means when CME, when the flux loop become unstable, they don't have time to produce a lot of twist there. Once they have some kind of twist, they're going to become unstable. So so when you say, you know, if it's twisted but not flux loop, no, if it's twisted, as only even has 1 turn, we say it is a flux loop already. So we don't need to be a slinky or many twists to qualify as a flux loop. Only, you know, 1 turn, similar to the shield arcade, you know, we can say it is a flux loop.
Yeah, okay. So the next question I have, actually, I'm always like thinking that, see, most of the time when we study flare and CME association, we understand that there is a magnetic energy release that is distributed into CME and flare. So if the same energy release is distributed into 2 phenomena called flare and CME, so why we see the correlation in the intensity of flare and kinematics? It should be contrary. Means when there is an intense flare, so most of the energy has gone into flare. So it means CME acceleration should be little slow. I am just thinking in this direction. Can you please comment on this?
No, there's no correlation between CME and the flare. So the correlation between the intensity of the flare and the velocity of CME is very poor. There's some studies on this. I think, you know, the people found out, you know, you do have cases of X-class flares and faster CMEs, right? But also you have cases of X-class flares, the slow CMEs. You also have cases of the you know, C-class flares, E-class flares, but CME is fairly fast. So if you look at the correlation with the flare intensity and the flare velocity, you can find a very large scattering. So the people have perception that the large flare associated with the fast CMEs, but the simple answer to that is the correlation is very poor.
Okay, but in your plot, like in 2006 paper, also the general trend you have shown is that yeah, the better correlation.
That is only timing. So the timing is very correlated. It's almost synchronized. So the timing of the flare, the timing of the CMEs, they are exactly synchronized, but the intensity they are not.
Okay, I
so
got
you could have, yeah, you could have a small flare at the same time occur as a CME, but the intensity, but the velocity could be different.
Okay.
The timing is always there, I think.
And follow up to this, so should we to understand the better driving mechanism, should we look the expansion of the CME rather than the propagation speed to correlate it with any energetic release process? So because the expansion will come mainly from the magnetic pressure. So means should we look more towards expansion than total propagation speed?
Yeah, well, I guess, you know, this is the question you should ask yourself, right? I know you have been looking into that, the expansion versus the So I think this is a very important topic. What drives expansion? What drives the acceleration? The two different things. So far, majority of studies have been focusing on CME acceleration, the leading edge, not cross section size. So you have done some work on the cross section, and then the expansion. But I don't think we have systematic study on this yet. But I think the timing of starting this kind of expansion is there, because the PSP Park Solar Probe has observed about a dozen CMEs. They're pretty small, but I think the observation is very close up. We can see a lot of detailed structure within the small CMEs near the sun. I think from these observations, the cross-section size can be determined very precisely. Before, we have hard time to study expansion because we don't know what's the size, right? The aspect ratio from these three, even with stereo observations from two angles, what is the aspect ratio of cross-section of the CME? The determination of this parameter is not accurate, I think. So that's why there's also limitation of understanding how the CME is expanding and how to explain that. But now I think we have we are having better data to address this issue.
Yeah. Okay. Yeah. Thank
you. I'm hoping you and your colleagues can look into the issue of expansion in the future.
Yeah. I will try. Yeah. Okay. Thank you.
Okay. So I see three raise hand, Dipankar, Rajguru, and Shatabda. So I will go one by one. So Dipankar, you can unmute and ask your question.
Yeah, thanks, Jan, for a very nice overview talk. I have two quick questions. One is, I was just wondering, you have not actually touched on the role of, magnetic flux emergence or rate of magnetic flux emergence in your, scenario of this, initiation process. To me, that seems to be quite an important aspect. So that's one question. The second, also, let me complete this for the brevity of time, is you showed lots of good examples of flux ropes now with the UV imaging devices. Now, we need also to follow up these flux ropes in the interplanetary space. Now, the question is, what do we see in the white light coronagraph images? Are they flux ropes or something else? Now, if that question is not resolved, all these, kinematics is going to be a big problem. So how do you plan to address that?
Yeah, Dipankar, nice to meet you. Nice to see you, online. Both of the questions you're raising, actually is also to my heart, because besides starting initiation process, it's also starting the evolution of the act region that lead to eruption. The days and weeks before, typically days and hours, how the magnetic field evolves toward the eruption. I have two PhD students graduated on this topic. But I didn't discuss today. But in these studies, commonly we found that the emergence of the flux, of course, provided the magnetic energy into the system. But they are not the key thing. The key thing is the flux cancellation. So you can have a lot of flux emergence, but that means that you're going to have eruption. You can have a lot of energy there. However, what it requires is the complexity of the eruption. And so if it's complex enough, then you have the multiple polarities, then you have the collision or the cancellation of the opposite polarity close to each other, then you end up with produce a flux loop, then you produce eruption. However, if you have a lot of flux, but it's a largely bipolar structure, as you know, if it's a bipolar structure, what happens with the two poles? They separate. So if they separate, in those cases, even though the sunspot is large. Hello?
Okay, Shamridhi, you please mute your microphone.
Oh, okay. So it's not asked question. Okay. Yeah. So for this big bipoles, you want to have big eruptions. So I think the complexity and the flux cancellation on the surface is the key, at least from some samples and examples we have studied. That's our impression. But I can't show you any data today. But it's interesting topic. And we are still working on this kind of thing. Regarding the post-eruption evolution flux of structure, of course, the flux slope we see, we only see flux slope at 1 AU in situ, right? That's the only thing we can see the magnetic field. We don't see the magnetic field from remote sensing observations in the corona. So EUV observations, white light observations are only show the features. So yes, so the flux will be is only coming out from the inference from in situ observations and also from the theoretical models. All the theoretical models predicting the flux forms after eruption. The white light observations can only for some events you can see the helical structure in white light, but not all of them. So basically, white light data does not prove that we see a flux over, but also the white light data does not against this scenario. And so still, I think we believe the underlying structure in white light CME is meant to be a magnetic flux loop, unless the models or data indicate otherwise.
Yeah, thanks. And somehow, that's the thing, what we see in white light and that linkage with the flux of what you see in UV, as you know, the density proportionality is very different in the two observing techniques. That also creates some more confusion into this. I think we have to somehow address that, which component of the CME structure we are seeing precisely in white light and which part we are seeing in UV, and how do we correlate them?
Yeah, and also I saw some latest the movies from the Whisper movie from PSP. There's one CME is very small, but since the spacecraft is very close to CME, it appears very large. You can see many slinky-like structures. Even for that a small CME close up when the resolution is very high. The data shows the indication of the many turns of the structure.
Yeah, recently, incidentally, Walker was showing some of the Whisper images of these flux ropes in a seminar in the same platform.
Oh, really? Yeah. Okay. Yeah, that was I guess probably saw the same thing. I think that was an interesting one to indicate even small CME could be a flux loop.
Thank you very much.
Yeah, but you want to see this in LASCO data very often.
So I see there are 3-4 more questions, and then G, it's maybe 2 o'clock in the morning for you, so it's okay if we go through a few more questions.
For me, it's okay. It's perfectly okay because I'm a late person anyway. Yeah.
Okay. Yeah. So Rajaguru, please.
Okay. Yeah. Thanks, Jayant. Hi, G. It's a very interesting talk. Thank you for this nice one. I'm not an expert in this field. I'm just trying to relate to what you said in the beginning of your talk in the first few slides about the statistics that among all the geomagnetic storms, which are somehow related to some eruptions on the sun, only less than 50% of them are with flares. And I'm just trying to relate that to your conclusions here now for the hot channel eruption. So is that the rest of the eruptions are filament? Is that the way to understand this in that number? So the hot channel eruptions are somehow associated with flares, and the other eruptions are just filament eruptions. Is that the way to understand this? Or?
Yeah. I think for the hot channel eruption because also limited by observations. For most of the CMEs or for most of the flares or eruptions, we don't see hot channel. So the hot channel can be only seen when the source region of the eruption is near between like 50 degrees from the central meridian and beyond, close to the limb. If such feature observed near disk center, it's very hard to see the hot channel. Because hot channel is just slightly brighter than the surrounding in the AIA 131. So regarding your question about the geomagnetic storms, only less than 50% are produced associated with a major solar flare. For the other events, for the other 65% of the events are not associated with a major solar flare. So what are they associated? Of course, they have to be associated with something from the polarity inversion line and also the flux rope. I think if I remember correctly, the maybe another 30% are associated with filament eruption. Then also there's a 15% they are not associated with anything.
Okay.
So there are about 15% of them, they are not associated with anything. What I mean, what I say not associated with anything is that there's no filament eruption on the disk as observed. There's no flare. There's no hot channel, of course. So this is so-called we call it a problematic event or the stealthy CME. Because some CMEs are stealthy. That is, you have CME eruption in the corona, seeing white light, but you don't see them in the low corona in EUV and H alpha. So such events does exist. So we do find that these stealthy CME can produce an intense geomagnetic storm. I think with the help of the stereo, probably we can address this issue. I think that some people, some studies on this already. I think they have the models of this stealthy CME, and I think they concluded that because the flux loop the initiated very high in the corona, not close to the surface of the sun. That's why you don't have any signature on near the disk, but it still have flux loop and it still have eruption.
All right. Okay. Jen, sorry, just one quick question. So just all the depictions of flux rope CMEs always show the 2 foot points still connected to the sun, far away. In the CME has reached far away, even close to the Earth. Is it always the case that the flux ropes are always connected to the sun, back to the sun?
It's in people's mind.
Okay.
This is in people's imagination. You always have a foot point connecting back to the sun. Observationally, no such evidence. Well, there's no strong evidence, but theoretically, you expect if it's a magnetic flux rope, you expect they are connected back to the surface of the sun. Yes, sure. For some events, you see the transient coronal hole or the theming regions of the CME are lasting for many hours. In some the ICMEs, you see the BDE, the bidirectional electron flow, in pitch angle distribution of supersome electrons. So this bidirectional flow is also indicating the connection to the photo point. But we know that for many ICMEs, you don't see such evidence of bidirectional flow. So, and also we look at the PSP CMEs, try to see the foot point. When you close up observation of CMEs, the foot point should stand out, right? But they are not. So yeah, so foot point, I think is interesting thing. People imagine they exist. They should exist by prediction, but observationally, it's harder to identify, I would say.
Yeah, thank you, Ji. Thanks.
Okay, Shatabda?
Yeah, thank you. First of all, thanks for the wonderful talk. So throughout the talk, we have been talking about this coherent magnetic flux rope, which is basically the framework of a CME. Now, my question to you is, what are your thoughts on the sustenance of this coherence of this flux rope structure as the CME is propagating through different heights? Now, the reason that I ask you this question is that in one of our recent works, we have been able to show that if you try to model the volume of the CME through different sections, let's say different section of the leading front and the legs of the CME, it seems that the volume is following different power laws. So that is kind of standing against this intuition that it is ceasing to, let's say that we are finding that it is ceasing to act as a coherent structure. So what is your thoughts on that?
Well, the coherency, of course, is a magnetic field, right? Magnetic field is a diverging free. So the continuity of the magnetic field is a natural thing to happen. Secondly, the helicity is conservation, right? So if it's a low beta plasma, in the corona, this coherency can be preserved pretty easily. Now the issue is that once these flux enter the solar wind, the solar wind is a high beta environment. So the flow dominates. Then the structure could be destroyed. So yeah, I think I'm not an expert on this coherency. I have not done any study on this, but my imagination is that the coherency will be lost on the way from the sun to the Earth. But then to what extent, that's up to modeling, I think. In situ observations show that, to identify a coherent flux slope at 1 AU is pretty difficult. Only small percentage of the ICMEs, maybe let's say 20%, have a perfectly coherent twisting or rotation, but the majority of them are kind of I would say is less organized as a simple flux loop.
Yeah, thank you.
Okay, actually there are two more questions on the chat, so I will read it to you. So question by Shesh, how the ambient magnetic field at the different level of corona affect the flux loop structure and its propagation?
The ambient field. The ambient field, there are two kinds of ambient field. One is that it's immediately surrounding the flux loop. That will be produced by the act region field if it's a flux loop come from act region. So this field will be a strapping field, will produce a stabilizer force to prevent the flux loop to escape easily until the flux loop grow and grow and grow, become large and become unstable, accumulate a lot of energy. So without this strapping field or ambient field, you want to have CMEs because basically any small energy accumulated will be gone, will erupt. You have to have this kind of overlying field to hold down the structure. Let the structure to conceive, to become bigger enough, then contain a lot of energy, when the structure becomes unstable, then it can get away. I'm not sure this is a question you want to answer. I want to ask the far away field. I'm not sure about it.
Maybe.
So okay. If you have any further question or clarify, you can type in, right?
Yeah. So there is no. So actually, there is one last question possibly from Sudhir, and his question is related to MHD stability triggered by fast reconnection or the stability triggering the MHD stability. So how can we identify which physical process is leading the cause of the triggering of the eruption?
Yeah, this is exactly what I want to say, but I'm not addressing. That is open question. So for the triggering, what is the trigger? Is the reconnection or is the instability? We don't know, and different people have different answer. But for me, I don't have an answer to that. I've been arguing with the people. The people talk is my good friend, but and also Bernhard Klim, and they come to visit us and visit them. We always argue about that. So we don't have a consensus on that. But nevertheless, during the impulsive phase, we believe these two processes are coupled. They have the mutually positive feeding back process among the two processes. But what triggers them, I don't know. And also, question to you guys, how can we use observation to distinguish the triggers if they happen at the same time? Because they do happen at the same time simultaneously. And then people are looking, try to see if the fast acceleration occurred before the flare or after the flare, but they don't find good evidence. They have the same harm. So that's why it's so difficult to distinguish the two triggers.
So
that's the open question.
I don't see any more questions. So
just I have a small question. I forgot to ask you that. So in one of your slides, you showed the equation for the Hooke force, flux of Hooke force,
Yes.
where I see some new terms which is different than the actual Tito-Demlin equation. So can you explain it more?
Yeah, I think if I can go back to.
Yeah. So I think is that paper from Olmedo and you 2010.
Yeah, that paper that is from the Olmedo, and yeah, he's my former student, and also from it came from Jim Chen initially. That equation.
Maybe later, I think.
Yeah, this one, I think. This is the equation.
No, there is an equation. You put equation FR, and that is a Hooke force equation. Yeah, here. So ring current.
Yeah.
So
So this equation is the first three terms 1, 2, 3, 4, 5. First 5 terms describe the Hooke force or Lorentz self force. The last term here describes the strapping force. Then there's a gravitational force and a drag force. So this is a whole equation for controlling the evolution of the flux loop.
Okay. Is this centrally coming from ring current? JP?
The ring current is from IT here. It's a toroidal current IT.
Okay.
So this ring current is there, and then combined with the curvature of the flux slope and cross section, produce the curvature force, basically the curvature producer force.
Okay, so ring current also causes this strapping force. Ring current is only.
The ring current, if the ring current is larger, the strapping force is also larger, because it's a Lorentz force. It's a J cross B. So if you have same overlying field, B field, you have higher current. Then you have more strapping force. But also it's also the increasing the self Lorentz force, the Hooke force. So it's a competition here.
Yeah. So, I think in the Tito and Demlin, so the strapping force is coming from the external bipolar field and as well as the line current. Okay, so I'm a little confused about this. So anyway, I will clarify myself after you give this one.
Yeah. The Tito Demlin is different model from this one. This is from Jim Chen's paper. There's no line current. There's no line current in this model.
Okay. Yeah, line current is giving more strapping force there, and it gives some more stability to the flux.
This one has nothing to do with the Tito-Demlin model.
Okay.
This is just the flux super model. Yeah.
Okay. Thank you.
So I don't see any more raised hand or any question in the chat. So we would like to thank the speaker again. So, and also all the audience to engage into this very detailed discussion. So I think there is a raised hand. I don't know, but let me see. So thank you very much. Thanks again, and giving talk on very unusual time for you. So thank you very much.
Yeah, it is my pleasure, and thanks for the invitation. I'm glad to give this presentation and have a lot of interesting discussion. I know you have a strong presence of sort of physics and heliophysics in your institute. So, and I know many of you, it's promising young. It's all young. There's many young promising scientists there. So, do a good job and keep in touch. And see you guys in.
Thank you. Thank you so much. Yeah.
Thank you.
Thank you very much.
Bye.
Thank you.
You're welcome. Bye-bye.
Okay, bye-bye.